Today what we're going to be doing is we're going to be starting to talk about fast reinforcement learning. So in terms of where we are in the class, we've just finished up policy search. You guys are working on policy gradient right now for your homework. And then that'll be the last homework, and then the rest of the time will be on projects. Excuse me. And then right now we're going to start to talk about fast reinforcement learning, which is something that we haven't talked about so much. So the things we've discussed a lot so far in the term are things like optimization, generalization, and delayed consequences. So how do we do planning and Markov decision processes? How do we scale up to really large state spaces using like deep neural networks? And how do we do this optimization? And I think that that works really well for a lot of cases where we have good simulators or where data is pretty cheap. But a lot of the work that I do in my own lab thinks about how do we teach computers to help us, which naturally involves reinforcement learning because we're teaching computers about how to make decisions that would help us. But I think there are a lot of other applications where we'd really like computers to help us. So things like education or healthcare or consumer marketing. And in each of these cases, we can think of them as being reinforcement learning problems because we'd have some sort of agent, like our computer, that is making decisions as it interacts with a person. And it's trying to optimize some reward. Like it's trying to help someone learn something, or it's trying to treat a patient, or it's trying to increase revenue for a company by having consumers click on ads. And in all of those cases, the place where data comes from is people. And so there's at least two big challenges with that. The first is that people are finite. There's not an infinite number of people. And also that it's expensive and costly to try to gather data when you interact with people. And so it raises the concern about sample efficiency. So in general, of course, we would love to have reinforcement learning algorithms that are both computationally efficient and sample efficient. But most of the techniques we've been looking at so far, particularly the sort of Q-learning type techniques, were really sort of inspired by this need for computational efficiency. So if we think back to when we were doing planning at the beginning, when we talked about doing dynamic programming versus doing Q-learning, in dynamic programming, we had to do a sum over all next states. And in TD learning, we sampled that. So in TD learning, we sort of had this constant cost per update versus for dynamic programming, we had this S squared times A cost. So it was much more expensive to do things like dynamic programming than it was to do TD learning on a per step basis. And so a lot of the techniques that have been developed in reinforcement learning have really been thinking about this computational efficiency issue. And there are a lot of times where computational efficiency is important. Like if you wanted to plan from scratch and you were sort of driving a car at 60 miles per hour, then if it takes you, so if you're driving a car at 60 miles per hour and it takes your computer 1 second to make a decision about how to turn the wheel or something like that, then during that 1 second, you've traveled, many feet. So in a lot of cases, you really do have real-time constraints on the computation you can do. And in many situations, like for, in the cases of some robotics, and particularly when we have simulators, we really want computational efficiency because we need to be able to do these things very quickly, and we can sort of use our simulators, but we need our simulators to be fast so our agent can learn. In contrast to those sort of examples are things where sample efficiency is super important and maybe computation is less important. So whenever experience is costly or hard to gather. And so this is particularly things that involve people. So if we think about students or patients or customers, like the way that our agent will learn about the world is making decisions, and that data affects real people. So it might be very reasonable for us to take, several days of computation if we could figure out a better way to treat cancer, because we don't want to randomly experiment on people, and we want to use the data as well as we can and be really, really sample efficient. Versus in the case of like Atari, we want to be really computationally efficient because we can do many, many simulations. It's fine, no one's getting hurt, but we need to eventually learn to make, to derive a good game. So one natural question might be, okay, so maybe now we care about sample efficiency, and before we cared perhaps more about computational efficiency, but maybe the algorithms we've already discussed are already sample efficient. So does anybody remember, like, on the order of magnitude, or on, like, somewhere in the rough ballpark, how many steps it took DQN to learn a good policy for Pong? Maybe there's multiple answers. Maybe someone raise their hand. Yeah.
5 million.
So maybe somebody guessed around 5 million. I think it varies somewhere probably between 2 to 10 is my guess. 2 to 10 million. So that's a lot of data to learn to play Pong. So I would argue that the techniques we've seen so far are not going to address this issue. It's not going to be reasonable for us to need somewhere between 2 to 10 million customers before we figure out a good way to target ads, or 2 to 10 million patients before we figure out the right decisions to do. So the techniques we've seen so far are not going to be, they're formally not sample efficient, and they're also empirically not sample efficient. So we're going to need new types of techniques than what we've seen so far. So, of course, when we start to think about this, we think about the general issue of, what does it mean for an algorithm to be good? We've talked about computational efficiency, and I've mentioned this thing called sample efficiency. But in general, I think one thing we care a lot about is, how good is our reinforcement learning algorithm? And we're going to start to try to quantify that in terms of sample efficiency. But of course, you could have an algorithm that's really sample efficient in the sense that maybe it only uses the first 10 data points and then it never updates its policy. So it doesn't need very much data to find a policy, but the policy is bad. So when we talk about sample efficiency, we're going to want both that we don't need very much data and that we don't need very much data in order to make good decisions. So we still want to get good performance. We just don't want to need very much experience to get there. So when we talk about what it means for an algorithm to be good, one possibility is we can talk about whether or not it converges at all. That just means whether or not the value function or the policies is stable at some point, like asymptotically, like as the number of time steps goes to infinity. And we talked about how sometimes with value function approximation, we don't even have that, like things can oscillate. Then another thing that's stronger than that you might want is to say, well, asymptotically, as t goes to infinity, will we converge to the optimal policy? And we talked about some algorithms that would do that under some different assumptions. But what we haven't talked about very much is sort of, well, how quickly do we get there? Asymptotically is a very long time. And so we might want to be able to say, if we have two algorithms, and one of them gets the optimal policy here, like if this is performance, this is time, and another algorithm goes like this, intuitively, algorithm 2 is better than algorithm 1, even though they both get to the optimal policy eventually. So we'd like to be able to sort of account for either, we can think about things like how many mistakes our algorithm makes, or its relative performance over time compared to the optimal. And so we'll start to talk today about some other forms of measures for how good an algorithm is. So in this lecture and the next couple of lectures, we're going to do several different things, trying to talk about sort of how good are these reinforcement learning algorithms, and think about algorithms that could be much better in terms of their guarantees for performance. We're going to start off and talk about tabular settings. In fact, today we're only going to talk about simple bandits, but generally for the next today and next lecture, we'll talk about tabular settings, and then hopefully also get to some about function approximation plus sample efficiency. But we'll start to talk about sort of settings, frameworks, and approaches. So the settings that we're going to be covering, like today and next time, is going to be bandits, which a number of you, who here is doing the default project? Okay, so a number of you are already starting to think about this in terms of the project. So we'll introduce bandits today, and then we'll also talk about this for MDPs. And then we'll also introduce frameworks. And these are evaluation criteria for formally assessing the quality of a reinforcement learning algorithm. So they're sort of a tool you could use to evaluate many different algorithms, and algorithms will either satisfy this framework or not, or have different properties under these different frameworks. And then we'll also start to talk about approaches, which are classes of algorithms for achieving these different evaluation criteria, or these different frameworks. in different settings, either for the MDP setting or for the bandit setting. And what we'll shortly see is that there's a couple main ideas of styles of approaches of algorithms, which turn out to both have be applicable both to bandit settings and MDP settings, and function approximation, actually, and also that have some really nice formal properties. There's sort of a couple big conceptual ideas about how we might do fast reinforcement learning. Okay, so the plan for today will be that we'll first start with an introduction to multi-arm bandits, then we'll talk about the definition of regret on a mathematical formal sense, and then we'll talk about optimism under uncertainty, and then as we can, we'll talk about Bayesian regret and probability matching and Thompson sampling. I'm curious, who here has ever seen this sort of material before? Okay, a couple people, most people not. Is it covered in AI? I don't think they would cover it. Oh, cool. Okay. All right, so for some of you, this will be a review. For most of you, it'll be new. So for multi-arm bandits, we can think of them as a subset of reinforcement learning. So it's generally considered a set of arms. There's a set of M arms, which are the equivalent to what we used to call actions. So in reinforcement learning, our set of actions, we're thinking of like there being M different actions. Now we're often going to call those arms. And then for each of those arms, they have a distribution of rewards you could get. So we haven't talked a lot about sort of having uncertainty over our rewards. We've mostly just talked about the expected reward. And for multi-arm bandits today, we're going to explicitly think about the fact that rewards might be sampled from a stochastic distribution. So there's some distribution that we don't know, which is conditioned on the arm. So conditioned on the arm, you're going to get different rewards. So for example, it could be that for arm 1, your distribution looks something like this. This is the probability of that reward, and this is rewards. And then for arm 2, it looks something like this. So in this particular example, the average reward for arm 1 would be higher than the average reward for arm 2, and then they would have different variances. But it doesn't have to be Gaussian. You could have lots of different distributions. Essentially, what we're trying to capture here is that whenever you take a particular action, which we also refer to as pulling an arm for the multi-arm bandit, then the reward you get might vary, even if you pull the same arm twice. So in this case, you can imagine that if you pull the arm once, arm 1 once, you might get a reward here, and maybe the second time you'd get a reward there. So the idea in this case is it's similar to MDPs, except for now there's no transition function. So there's no state, or equivalently, you can think of it as there's only a single state. And so when you take an arm, you stay in the same state. There's always these M actions available to you. And on each step, you get to pick what action to take, and then you observe some reward that is sampled from the unknown probability distribution associated with that arm. And just like in reinforcement learning, we don't know what those reward distributions are in advance, and our goal is to maximize the cumulative reward. So if someone told you what these distributions were in advance, you would know exactly which arm to pull, whichever one has the highest expected mean. So we're going to try to use pretty similar notation to what we had for the reinforcement learning case. But if you notice things that are confusing, just let me know. So we're going to define the action value as the mean reward for a particular action. So that's QA. This is unknown. The agent doesn't know this in advance. The optimal value, B star, is going to be equal to Q of the best action. And then the regret is going to be the opportunity loss for one step. So what that means is that if instead of taking, if you could have taken Q of A star, and instead you took Q of AT, so this is the actual arm you selected, how much in expectation did you lose by taking the suboptimal arm? And this is how we're going to mathematically define regret in the case of reinforcement learning. So if you selected the optimal arm, your expected regret would be 0 for that time step. But for any other arm, there will be some loss. And the total regret is just the total opportunity loss if you sum over all the time steps that the agent acts and compare the actions it took and the expected reward of each of those actions to the expected reward of the optimal action. So just to be clear here, this is not known. This is not known to the agent. And this is unknown to the agent. Just to check for understanding for a second, why is this, so why is the second thing unknown to the agent? Yeah.
Because you don't know the probability distribution.
Right. So that's correct. So you don't know what the distribution is. So you don't know what Q is. You get to observe a sample from that. So you get to observe R. You get to get an R, which was sampled from the probability distribution over words, given the action that was taken. But you don't get to observe either the true expected value of the optimal arm, nor the true expected value of the arm that you selected. So this isn't something we can normally evaluate unless we're in a simulated domain. Okay. But we're going to talk about ways that we can bound this and think about algorithms that try to minimize the regret. So if we think about ways to sort of quantify it, another way to think about it alternatively is that think about the number of times that you take a particular action. We can call that NT of A. So that's like the number of times we select action 1, action 2, etc. And then we can define a gap, which is the difference between the optimal arm's value and the value of the arm that we selected. And that's the gap. So that's how much we lost by picking a different arm than the optimal arm. So this gap is equal to, gap for A star is equal to 0, because you don't lose anything by taking the optimal arm, and for all other arms it's going to be positive. So another way to think about the regret, which is equivalent, is to say this is equivalent to thinking about what are the expected number of times you select each of the arms times their gap. So how much you would lose by selecting that arm compared to the optimal arm. And what we would like is that sort of an algorithm should be able to adjust how many times you pull arms which have large gaps. So if there's a really, really bad arm, like there's really bad action which has a very low reward, you would like not to pull that as much, to take that action as much as the arms that are close to optimal. So one approach that we've seen before is greedy. In the case of bandits, the greedy algorithm is very simple. We just average the rewards we've seen for an arm. So we just look at every single time that we took that arm, we look at the reward we got for each of those timestamps, and then we average it. And that just gives us an estimate of Q hat. And then what greedy does is it selects the action with the highest value and takes that arm forever. So it's probably clear in this case that because the rewards are sampled from a stochastic distribution, that if you are unlucky and get samples that are misrepresentative, then you can lock into the wrong action and stay there forever. So if we think of that little example I gave before, and I'll work out a bigger example shortly. So in this case, imagine this is reward, this is probability, and this was A2. So let's imagine that the first, and I don't know, I'll make this 1 and this 0. So if you sample from A1, in this case, you could imagine there's some non-zero probability that the first sample you get is, say, 0.2 for A1, and the first sample you get for A2 with non-zero probability might be 0.5. So the true mean of A2 is lower than the mean of A1, but if you sampled each of these once, then if you were greedy with respect to that, then you would take the wrong action forever. Yeah.
Wrong action forever. Is the idea that our policy is going to be influencing what samples we'll get in the future, or is the idea, but there are some set of samples independent of this greedy policy to begin? Because it would seem otherwise, if there's non-zero reward, you just take that one forever.
Great question. So yeah. So what I said is, is there an additional thing that we're doing kind of before this? Normally, for a lot of these algorithms, we're going to assume that all of them operate by selecting each arm once, at least if you have a finite set of arms. And equivalently, you can say if you don't have any data, you treat everything equivalently. But essentially, most of these ones say until you have data for all the arms, we're going to do round robin. You're going to sample everything once. And after you do that, either you can be greedy or we can do something else. So there has to be a pre-initialization phase. It's a good question. So, and we're also going to assume for right now that we split ties with equal probability. So if there are two arms that have the same probability and they both have the max value, then you would split your time between those until the values changed. So this is an example where if we first sampled A1 once, then sampled A2 once, and because there's a non-zero probability that those samples would make it look that action A1 has a lower mean than action A2, then you could lock into the wrong action forever. Now, an E-greedy algorithm, which we've seen before in class, does something very similar, except for with probability 1 minus epsilon, we select the greedy action, and otherwise with epsilon, we split our probability across all the other actions, or all the other arms. So in these cases, we have some more robustness. So in this case, we would continue to sample the other action, but we're always going to make a suboptimal decision at least epsilon% of the time. Well, approximately. It's a little bit less than that because if you do it totally randomly, but it's order epsilon. I mean, it's slightly less than that because if you uniformly split across all your arms with 1 over the number of arms probability, you will be selecting the optimal action. Okay, so let's see these in practice for a second before we talk more about better algorithms. So let's imagine we're trying to figure out how to treat broken toes, and this is not a real medical example, but let's imagine there's three different options. One is surgery. One is buddy taping the broken toe with another toe, which is what the internet might tell you to do. And the third is to do nothing. And the outcome measure is going to be a binary variable of whether or not your toe is healed after 6 weeks, as assessed by an X-ray. Okay, so let's imagine that we model this as a multi-arm bandit with 3 arms, where each arm corresponds to, well, I'll ask you in a second what it corresponds to, and there's an unknown parameter here. So each arm, there's an unknown parameter, which is the reward outcome. So let's just take 1 or 2 minutes just to say, what does a pool of an arm correspond to in this case, and why is it reasonable to model it as a bandit instead of an MDP? Yeah.
And in terms of why we model it as a bandit, one reason is that MDPs usually think of an agent walking through the world, and the world has many different states, and we analyze those. Here we have just one state, a toe is broken, and various actions that you can run.
That's right. That is correct. So here we just have one thing, and so what does it mean to pull an arm in this case or take an action? What does that correspond to in the real world?
That would be a new patient coming in and then making a decision about the care for that patient.
Right. So that's like a patient coming in and then us deciding to either do surgery on them or giving them, in this case, doing one of the 3 options for treatment. And so in this case too, each pool is a different patient. So how we treat patient 1 isn't going to generally affect how we treat patient 2 in terms of whether they healed or not, or whether that particular surgery worked for them. Doesn't affect the next patient coming in. So all the patients are IID. And what we want to figure out to do is which of these treatments on average is most effective. Okay, so let's think about these in a particular setting. So a particular set of values. So let's imagine that they're all Bernoulli reward variables because either the toe is going to be healed or it's not going to be healed after 6 weeks. Turns out in this particular fake example, surgery is best. So if you do surgery with 95% probability, it'll be healed after 6 weeks. Buddy taping is 90% and doing nothing is 0.1. So what would happen if we did something like a greedy algorithm? Oh, yeah.
Incorporate other factors into pulling the arms, for example, surgeries like taxing, or can be cost ineffective versus buddy taping? Are there ways to incorporate that?
Yeah, it's a great question. So Question is about like, could we, surgery is a lot more invasive and there might be other side effects, et cetera. There's a couple different ways you could imagine putting that information in. One is you could just change the reward outcome. So you could say, maybe it's more effective, but it's also really costly and I've got to have some way to combine outcomes with cost. Another thing that one might be interested in doing in these sorts of cases is that you might have a distribution of outcomes. So in this case, all of them have the same distribution. They're all Bernoulli. But in some cases, your reward outcomes will be complicated functions, right? Like, so it might be that maybe for some people, surgery is really awful, and for most people, it's really good. But it's really bad for some people because they have, some really bad side effects. And so its mean is still better. But there's like this really bad risk tail of like maybe people, react badly to anesthesia or something like that. So in those cases, you might want to not focus on expected outcomes. You might want to look at risk sensitivity. And in fact, one of the things that we're doing in my group is looking at safe reinforcement learning, including safe bandits, and thinking about how you could optimize for risk-sensitive criteria. Another thing that we're not going to talk about today, which you also might want to do in this case, is that patients are not all identical, and you might want to incorporate some sort of contextual features about the patient to try to decide which surgery to do, or surgery versus buddy taping. And hopefully, those of you who are doing the default project will think about this definitely, and we'll probably get to this in a couple lectures. So in general, we often have sort of a rich contextual state, which will also affect the outcomes. Okay, so in this case, let's imagine that we have these three potential interventions that we can do, and we're running the greedy algorithm. So as brought up before, we're going to sample each of these arms once, and now we're going to get an empirical average. So let's say that we sample action A1, and we get a +1. And so now our empirical average of what the expected reward is for action A1 is 1. And then we do A2, and we also get 1, so that's our new average. And then we do A3, we get a 0. And so at this point, what is the probability of greedy selecting each arm, assuming that ties are split randomly? Yeah.
2 for the first two, then epsilon for the third one, like plus or minus a little
And
bit.
remind me? Yeah, so what Michael said is exactly correct for the E-greedy case, so you're jumping ahead a little bit, but that's totally right. In this case, for greedy, it'll just be 50-50. Yeah, you're already moving to E-greedy. So yeah, so the probability of A1 is going to equal to probability of A2, which is going to equal to 1/2. So let's imagine that we did this for a few time steps. So we can think about what the regret is that we incur along all of this way. So at the beginning, we have this sort of initialization period where we're going to select each action once. And we're always comparing this to what was the reward we could have gotten under the optimal action. So the regret here is going to be exactly equal. So this is optimal. And remember, the regret is going to be Q of A star minus Q of the action you took. So in the first case, it's going to be 0 because we took the optimal action. In the second case, it's going to be 0.95 minus 0.9, which is 0.05. And in the third case, it's going to be 0.95 minus 0.1. And then in the third case, it's going to be 0, or fourth case is going to be 0, and then it's going to be 0.05 again. Now, in this situation, will we ever select, in greedy, will we ever select A3 again, given the values we've seen so far? No. Yeah, I see people say no. No, so why not? Is it possible, what's our current estimate of the reward for A3? 0. Yeah, so I guess I didn't put those here, but this was the actual, these were the rewards we got. So it was 1, 1, 0. So our current estimate for A3 is 0. We know our rewards are bounded between 0 and 1. None of our estimates can ever collapse below 0. And we already have a positive 1 for these other two actions, which means that their averages can never go to 0. So we're never going to take A3 again. Now, in this case, that's not actually that bad. Like here that's not actually a problem because A3 is a bad arm and it's got a much lower expected reward. In other cases, it could be that A3, we just got unlucky. And in that case, it could mean that we never take the optimal action. Yeah.
I thought we used star like in terms of the reward for regret.
Yes, and that's the same as this. Good question. So this is the same as B star. Yeah. And I'll go back and forth between notation, but yeah, definitely just ask me. So in this case, we're never going to select A3 again. And now notice that in the greedy case, there are cases where if I had used slightly different values here, that you might have selected A3 again later. Because if it's the case that, like if you didn't have Bernoulli rewards, but you had Gaussians, it could be that the rewards for other arms drop below another arm later, and then you start to switch. So you don't necessarily always stick with which other arm looked best at the beginning. But in this particular case, with these outcomes, then you're not going to select A3 ever again. All right, now let's do eGreedy. So in this case, we're going to assume we got exactly the same outcomes for the first few. And then what said is that we're going to have 1/2 minus epsilon over 2. So we're going to split ties randomly again. So with probability epsilon, we're going to take, with epsilon over 3, we're going to take A1 or A2 or A3. And with 1 minus epsilon over 2, we're going to take A1 or A2.
It's not updating.
Interesting. Okay, so in this case, it's going to look almost identical, except we're still going to have some probability of taking A3 in this case. And we can do a similar computation here. In this case, we've assumed that all of these are exactly the same. So eGreedy in this case will select A3 again, yes. If epsilon is fixed, not updating again. If epsilon is fixed, how many times is it going to select A3? The main question is whether it's finite or infinite. So maybe talk to a neighbor for a second and decide whether, if epsilon is fixed, whether it'll be, A3 will be selected a finite or infinite number of times, and what that means in terms of the regret. Okay, I'm going to have everybody vote. So if you think it's going to be selected an infinite number of times, raise your hand. Great. So what's that mean in terms of regret? Is the regret going to be good or bad?
It's unbounded.
Great. Bad regret. I mean, in general, regret is going to be unbounded, unfortunately, in these cases. So we're always going to, unfortunately, have infinite regret. But the rate at which it grows can be can be much smaller, depending on the algorithm you do. So in particular, and yeah, so we can also think about it in this case. So if you have a large gap, which we do for A3 here, and we're going to be selecting that arm an infinite number of times, then eGreedy is also going to have a large regret. So I like this plot. This plot comes from David Silver's slides. So if you explore forever, like if you just do random, which we didn't discuss, but you could also do, then you're going to have linear total regret, which means that with a number of time steps t, you're going to scale linearly with t. Essentially, your regret is growing unboundedly, and it's growing linearly, which is essentially proportional. I mean, it's going to generally have a constant in front of it, but it's going to be a constant times the worst you could do at every time step. Because if you always select the worst arm at every time step, your regret will also grow linearly. So it's pretty bad. If you explore never, if you do greedy, then it also can be linear. And if you do eGreedy, it's also linear. So essentially, it means that all of these algorithms that we've been using so far can have really, really bad performance, certainly in bad cases. And so the critical question is whether or not it's possible to do better than that. So can we have what's often called sublinear regret? So we want to have regret. If an algorithm is going to be considered good in terms of its performance and its sample efficiency, we're going to want its regret to grow sublinearly. When we think about this, we're generally going to think about whether the bounds that we create, and the performance bounds, are going to be problem independent or problem dependent. So most of the bounds, it depends a little bit. For MDPs, most of the bounds that we can get are going to be problem independent. For bandits, there's a lot of problem dependent bounds. Problem dependent bounds in the case of bandits mean that the amount of regret that we get is going to be a function of those gaps. And that should be sort of intuitive. So if you have, let's imagine that we just have two arms, like A1 and A2, and the mean, the expected reward. So if this is, the expected reward is 1, and this is expected reward of 0.001, intuitively it should be easier to figure out that arm 1 is better than arm 2 than if this is like 0.53 and this is 0.525. Because in one case, it's really hard to tell the difference between the mean of the two arms. In the other case, the means are really, really far apart. So somewhat intuitively, if the gap is really large, it should be easier for us to learn. And if it's really small, it should be harder. Yeah.
So if optimal reward is deterministic for some actions, I mean we have 0 regret.
Good question. Question is, if the optimal reward is, are you just saying optimal reward? Yeah. The optimal reward is deterministic. Do we have 0 regret? If you know it. So if you know that all the rewards of the arms are deterministic, then you just need to pull them once, then you can make a good decision, and then you're done. In general, these algorithms aren't going to know that information. If you don't, even if it was deterministic, you're still going to have these other forms of bounds.
So what about in the greedy case then?
If it's determined, if in the greedy case, it's a good question. In the greedy case, if your real rewards are deterministic, then you would have pulled all arms once, and you will make no mistakes. You'll have 0 regret basically from that point onwards. So we'd consider that as just like you'd have some initial constant regret, and then afterward it would be independent of t. Did you have a question?
Yeah.
Remind me your name.
Is it also a function of the variance of each arm?
Oh, great question.
In that case, like the second arm had like a massive variance.
Yeah, great question. So we're not going to talk. The question is whether it also depends on the variance in addition to the mean. Yes, we're not going to talk about that. But in addition to problem-dependent bounds, you can certainly think about parametric. Like if you have some parametric knowledge on the distribution of the rewards, then you can exploit it. So if you know it's a Gaussian or other things like that. I think in general, if you know like if you have information about the moments, then you should be able to exploit it. Most of the information I've seen is looking at the mean and the variance. We very frequently, throughout a lot of this stuff, are going to assume that our rewards are bounded. That's going to be important for most of the proofs that we do, even without making any other parametric assumptions. Okay, but then the other version of this is problem independent, which just says, regardless of the domain you're in and regardless of the gaps, can we also show that regardless of any structure of the problem, can we still ensure that the regret grows sublinearly? And that's what we're going to mostly focus on today. So I think lower theoretical bounds are helpful to try to understand how hard a problem is. So I said, is it possible for something to be sublinear? And there's been previous work to look at sort of, well, how much does the regret have to grow? So in this case, this is regret. We're mostly going to write out regret. But in this case, they prove that in terms of the gaps and the similarity in the distributions in terms of the KL divergence, that you can show a lower bound on how much regret grows. So this is where the sort of unfortunate aspect of regret growing unboundedly comes up. If you don't make any other assumptions on the distributions of your rewards, in general, the regret of your regret will grow unboundedly, and it will do so in terms of these gaps and the KL divergence. But it's still sublinear, so that's nice. So it's growing logarithmically with t here. T is the time steps. It's encouraging that like our lower bounds suggest that there's room for traction, right? That we can definitely, at least there's no formal result that says it has to be linear. It says, no, we should be able to grow much slower. So how would we maybe do this? So this is now, we've talked about a particular framework, which is regret. We talked about a setting, which is bandits. And now we're going to talk about an approach, which is optimism in the face of uncertainty. And the idea is simply to choose actions which might have high value. Why should we do this?
I had a question on the limit in the previous slide. Sorry, is that true at every t or only in the limit? Because as it's written, isn't that just saying that it's greater than infinity?
That's a good question. The question is about whether it holds. I think this holds on every time step. I'd have to check the exact way that they wrote this. There's also constants, but I think this should hold on a per time step basis.
So we're really saying that as time is going along, this should be true.
Yeah, the limit as t goes large, this is where I'd have to look back at the original paper. There's probably additional constant terms which are transitory. And so this is probably the dominant term as t goes large. But in a lot of the regret bounds, particularly in our MDP cases, we often have transitory terms that are independent of the time step, but are still large early on. That's my guess, but great question. Okay, so optimism in the face of uncertainty says that we should choose actions that might have a high value. Why? Well, there's two possible outcomes. If we pick something that we think might be good, one is it's good. So if it is good, or I'll be more precise in this case. So let's say we select, so A1, and one is A1 has high reward. So that's good. If we took an action, it actually does it, and because we thought it might have high reward, and it actually does have high reward, then we're going to have small regret. So that's good. What's the other outcome? A1 does not have high reward. When we sample this, we get an R for A1 with low reward. Well, if we get something with low reward, we've learned something. So we're like, hey, we tried that restaurant again. We thought it was great the first time. The second time, it was horrible. So now we've learned that that restaurant is not as good, and we update our estimate of how good that restaurant is. And that means we don't think that that action has as high a value as it did before. So essentially, either the world really is great, and in which case that's great. We're going to have low regret. Or the world is not that great, and then we learn something. So this gives us information. And so this acting optimistically gives us both information about the world or allows us to achieve high reward. And so it turns out to have been a really nice principle. It's been around since at least Leslie Cabling in 1993 introduced this idea of sort of interval estimation. And then there started to be a lot of analysis of these types of optimism under uncertainty techniques. So how could we do this more formally, or where would we get to be more precise about what it means for an action to have a high value? Let's imagine that we estimate an upper confidence bound for each action value, such that the real value of that action is less than or equal to the upper confidence bound with high probability. And those upper confidence bounds in general are going to depend on how many times we've selected that particular action. Because we would like it to be such that if we've selected that action a lot, that upper confidence bound should be pretty close to Q of A. And if we haven't selected it very much, maybe we're really optimistic. And then we can define an upper confidence bound bandit algorithm by just selecting whichever action has the highest upper confidence bound. So for every single action, we maintain an upper confidence bound, and then we just select whichever one has the max, and then we update the upper confidence bound for that action after we take it. So a UCB algorithm would, for t equals 1, ... we would first have an initialization phase where we pull each arm once. And then we compute ut of at for all a. And then for t equals 1, ... we would select at equaling this argmax. And then we would get a reward that is sampled from the true reward distribution for that arm. And then we would update UT of AT. And all other arms. Turns out that often we have to update not just the action of the arm that we took, but the action of all the other arms we took too. And this basically comes into, you don't have to do that, but in terms of the theory, we often have to do that in order to account for high probability bounds. And we'll see more about that in just a second. So every time you get a reward, you update the upper confidence bounds of all your arms, and then you select the next action and you repeat this just over and over again. Okay, so how are we going to define these U of t? So we're going to use Hopting's inequality. It's a refresher. In Hopting's inequality, we can apply this to a set of IID random variables. We're going to assume right now that all of them are bounded between 0 and 1. And we're going to define our sample mean just to be the average over all of those variables. And then what Hopting says is that the probability that that expected mean is, like, this is the true expected mean. So this is the true mean. This is our empirical mean. And this is, you can think of this as like some epsilon. This is just some constant. Is the probability that your true mean is greater than the empirical mean plus some constant u is less than or equal to the exponential minus 2n mu squared. So this is the number of samples we have. Okay. So we can also invert this to say if you want this to be true with a certain probability, you can pick a mu so that xn plus mu is going to be at least as large as the real mean. So let's say what we want to do is we want that the empirical mean plus mu, the probability that that's less than the real mean, to equal to delta over t squared. And we'll see why we might want to choose that particular probability shortly, but let's imagine for a second that's what we want our probability to be. So then we can solve for what mu has to be. Okay, so that's exponential minus 2n mu squared has to equal to delta over t squared. And then what we do is we just solve for what mu is. Thanks for letting me know. Okay, so mu in this case is going to be equal to the square root 1 over 2n log of t squared over delta. So I just solved for that equation. And what does that tell us? That says that if we define our ut of, or in this case, we define, I'll keep with the same notation as for Hopting. So if we have x n plus mu, with that particular choice of mu, that's generally going to be greater than or equal to the true expected value of x with probability greater than or equal to 1 minus delta over t squared. So this Hopting inequality gives us a way to define an upper bound. Because instead of these being x's right now, you could imagine those are just pools from our arm, and those are all rewards. And so this says if you take your empirical average of your rewards so far, and you add in this upper bound, which depends on the number of times we pulled that arm, and t. So t here, notice, is the total number of time steps we pulled any arms, and n is the number of times we pulled that arm. So they're not the same thing. So we're inside of this confidence bound, we have a confidence bound that is decreasing at a rate of how many times we pulled this particular arm. And then we have a log term, which is increasing at the rate of the number of times we pulled any arm. And that is the reason why after each time step, we have to update the upper confidence bounds of all the arms. So you kind of have these two competing rates that are going on. As you pull an arm more, you're going to get a better estimate of its reward. So it's shrinking. But then you also have this slower growing term, this log, which is increasing with the number of time steps. Okay. All right, so this is one way we could define our upper confidence bounds. So we could use this in the case of our rewards. So we might want to say that ut of at is equal to our empirical average of that arm plus 1 over 2 the number of times we pulled that arm times log of t squared divided by delta. So this is how one way for us to define our upper confidence bounds. All right. So now the next question is, okay, so we've done that. How is that going to help us in terms of showing that maybe the regret of something which is optimistic is actually sublinear? Okay, so what we're going to do now is, I'll do a quick poll. Do you guys want me to write it on here, or do you guys want me to do it on the board? So raise your hand if you want it on the board. All right, raise your hand if you want it on here. Okay, we'll do this next part on the board. That was easy. Was there a question in the back?
Yeah, just a quick question. I'm a little confused in this derivation about t, because it seems like
About
when you
what?
first introduced it, about t.
Yes.
It seemed when you first introduced it, it was basically a constant that we moved around, but then later you were saying that that's actually the time that we're updating every time step. So how are we able to do that?
Yeah, it's a good question. So you're right, and I'm being slightly imprecise about this. If you know what the time horizon is that you're going to be acting in an bandit, you can set t to be the maximum. So if you know that you're going to act for t time steps, you can plug that in. And then your confidence bounds then that log term is fixed, basically. In online settings, if you don't know that, you can also constantly be updated with the time step. It's a good question. Yeah.
How is delta decided?
Pardon?
How is delta? What is delta?
Oh, good question. Question is, what is delta? What we're gonna, I did not tell you. In this case, it's telling us, it's specifying what is the probability this is holding, like what this inequality is holding. Later, we're gonna provide a regret bound that is high probability. So we're gonna prove a regret bound, which is something like with probabilities 1 minus a function of delta, your regret will be sublinear. So that's, you can get expected regret bounds too, and the UCB paper, which one of the original UCB papers, provides an expected bound, but I thought it was this bound was a little bit easier to do in class, so I thought I would do the high probability bound. Yeah.
So before when we were talking about regret, I didn't exactly understand how you use regret to update your estimate of the action value.
Oh, good question. So the question is, do we use, or how would we use the regret bound to update our estimate action? We don't. Regret is just a tool to analyze our algorithm. Great clarification. So regret is a way for us to analyze whether or not an algorithm is going to be good or bad in terms of how fast the regret grows, but it's not used in the algorithm itself. The algorithm doesn't compute regret, and it's not used in terms of the updating. Excuse me. Okay, so actually I'll leave this one up here so you guys can continue to see that. All right, so let's do our proof. So what we're going to want to do now is we're going to want to try to prove something about the regret, but before, and how quickly it grows for the upper confidence bound algorithm. But before I prove that, I'm going to try to argue to you that we're going to look at sort of the probability of failure of these confidence bounds. So what I've said here is that we're going to define these upper confidence bounds like this, in terms of the empirical mean for that arm so far, plus this term that depends on the number of times we pull that arm. And what I want to convince you now is, what is the probability? What is the probability that on one step, that on some step, the confidence bounds will fail to hold? The confidence bounds will fail to hold. Why is this bad? Okay, so we want to bound the probability that on any step, as we're running our algorithm, that our confidence bounds fail to hold. Why? Because if they all hold, we can guarantee we're going to be making some, we're going to have some nice properties. Okay, so note, if all the confidence bounds hold, like on every step, then we can ensure the following. So if all confidence bounds hold, then UT of AT, this is the actual arm we selected, is going to be greater than Q of A star. The real value of the optimal arm. Okay. So why is this true? There's two cases here. Either AT is equal to A star, or AT is not equal to A star. So let's just take a second and maybe talk to your neighbor to say, if it's the case that our confidence bounds hold, which means that really is the case that we have that this confidence bound is going to be greater than or equal to the mean for that arm. So these are true confidence bounds. This equation is holding. We're not getting a failure. So we know that QT, which is this, is going to be greater than the real expected value for that arm. Okay, so if that's true, then this is going to hold at every time step. So maybe let's take a neighbor. If it's not clear what I'm asking or how to think about that, feel free to raise your hand too. So there's two cases. Either the arm that we selected is A star or the arm we selected is not A star. And in both cases, this is going to hold if the confidence bounds are correct. So maybe let's take a second to think about this, or feel free to raise your hand if it's not clear how to get started on that. And let me just be clear here. So I just wanted to note at the top there that if the confidence bounds hold, then that upper confidence bounds, which is equal to that, is going to be greater than the real expected value for that arm. Yeah.
On the confidence bound that you have, or the equation you have written over there.
Yeah.
So you're saying that the optimal, like your optimal Q value should be less than all the confidence bounds for any action.
No, good question. So asked me to clarify what's this is saying for the arm that you selected, the upper confidence bound of the arm you selected has a value that upper confidence bound that you used to choose the arm, whichever arm you selected, the upper confidence bound of that arm is higher than the true value of the optimal arm. That's what this equation is saying. Saying that if the confidence bounds hold on all time steps, which they might not, but let's say that they do, because these are only high probability bounds, but if they hold on all time steps, then whatever arm you selected, its upper confidence bound is higher than the value of the true arm, the real value of the true arm. Okay. And I just wanted to be clear what I mean for the confidence bound to hold. I put this up there. So that means that the upper confidence bound of an arm holding means that that upper confidence bound, which is defined in that way, is greater than the true value of that arm. So let's work through this a little bit. So let's see, there's two cases. So if AT is equal to A star, then that's what this is saying is UT of A star greater than Q of A star? Does that hold if the confidence bounds hold? Yes, by definition. So if you look up there, so the upper confidence bounds, if it holds for an action, the upper confidence bound for an action has to be bigger than the mean for that action if that upper confidence bounds hold. Okay, so this works. So if we really selected the optimal action, we've defined our upper confidence bounds so they really are better than the mean of that arm. And so this holds. The other case is that AT is not equal to A star. So what does that mean? That means that UT of AT is greater than UT of A star. because otherwise we would have selected A star. It means that some other arm had a higher upper confidence bound than the optimal action, and we know that this is greater than Q of A star. Okay. So if the confidence bounds holds, we know at every single time step the upper confidence bound of the arm we selected is better than the true mean of the optimal arm. Yes?
Epsilon greedy case as well.
This is true in epsilon greedy case as well. So I don't follow your question yet.
So, yeah, like, you're selecting this arm using some strategy, right?
Yeah.
And in this case, maximizing action reward, right?
No, UT. So this only holds, this part only holds because we're picking the argmax, you're not going to be able to see this, but the argmax A of UT of AT. So that first inequality only, well, there might be other algorithms it holds for too, but it holds in particular for the upper confidence bound. Great question. Okay, so this says, if we could get it, and we'll see shortly why that matters, but kind of intuitively, this says, if the confidence bounds hold, then we know that the upper confidence bound of the arm we select is going to be better than the optimal arm. And the reason we're going to want that is later when we're doing the regret bounds, we do not want to deal with properties we don't observe, namely the value of the optimal arm, because we don't know what Q of A star is. We don't know which arm it is. So when we look at regret bound, right now regret bounds are in terms of Q of A star. We don't know what that quantity is. So we're going to need to figure out some way to get rid of that quantity. And we're going to end up using these upper bounds. But we're going to need the fact that the upper bound of the arm we select is better than the Q of A star. Okay, so this is saying that that's true if our upper confidence bounds hold. What is the probability that that occurs? Okay, so what that means is if we want to say that on all time steps, this is a union over events. A union over all the events for t equals 1 to t of the probability that Q of A star minus the upper confidence bound of the action that we took. We want this, oops, not that way. We want the probability of this, which is essentially the probability of failure. So this says, this is if all confidence bounds hold, things are good. This says, what is the probability that that failed? That the arm that you took actually is not better, the upper confidence bound is not better than the real mean of the optimal arm. So this is the failure case where the confidence bound, we're going to say that if we look at that, we don't want this thing to happen. We can upper bound that by making sure our upper confidence bounds hold at all time steps. So these are the arms. So what I said up there is that if all of our confidence bounds hold on all time steps, we can ensure that. So we're now going to write that down in terms of what's the probability that the upper confidence bounds do hold on all time steps. And so we're going to do probability that Q of AT as Q hat of AT is greater than U. Okay, this is the upper confidence bound we defined over there. This is just saying that the upper confidence bound holds for each arm on each time step. Okay. Well, by definition over there, we said we picked an upper confidence bound to make sure this held with at least probability delta over t squared. Because that's how we defined our upper confidence bound. We picked a big enough thing to add on to our empirical means so that we could ensure that that upper confidence bound really was larger than our mean. So now we have a union over all time steps, a union over all arms, delta divided by t squared. And note that if you sum over t equals 1 to infinity of t to the minus t, that's equal to pi squared over 6. Which is less than 2. So when you do this sum, you get 2m delta. So what this says is that the probability that your upper confidence bounds hold over all time steps So this is the negative, this is that they don't hold, is at least 1 minus 2m delta. So all our what we're going to end up doing is we're going to have a high probability regret bound that says with probability at least 1 minus 2m delta, you're going to get a small regret. Yeah. Great question. Yes, this is all for an infinite horizon case. We're going to look at we're going to find our regret in terms of t, the number of time steps. Okay. All right, so why is this useful? Do you guys want me to leave this up or we can move that now? Everyone's written it down who wants it. Okay, so can this go up? Let me see. Or not. Okay, so why is this useful? Okay, we're now going to define our regret. So this part of the board just says that we've made it so these upper confidence bounds holds with high probability. Now we're going to try to show what our regret is going to be. Oh, good. Okay. Thank you. All right, so what's our regret? Regret of our UCB algorithm after t time steps is just equal to the sum over all those time steps, t equals 1 to t of q of a star minus q of at. Okay. Remember, we don't know either of these things. We don't know what the real mean is of any arm we pick, and we don't know what the real mean is of the optimal arm. So we need to turn this into things that we know. These are unknown. Okay. So what we're going to do is one of our favorite tricks in reinforcement learning, which is we add and subtract the same thing. So we do sum over t equals 1 to t of ut, this upper bound, at, minus q of at, plus q of a star, minus ut at. I just added and subtracted the same thing. I picked the upper confidence bound of the arm that we selected at each time point. Okay, so then the important thing is that what we showed over here is that if all of our confidence bounds hold, then the upper confidence bound of the arm we selected is larger than q of a star. That's what we showed over there. So that means that this has to be less than or equal to 0. Because the upper confidence bound of whatever arm we selected, we proved over there, is going to be higher than the real mean of the optimal arm. So this second part of this equation is less than or equal to 0, which means we can up or down our regret as follows. So now we can drop that second term. So that's nice, right? Because now we don't have any A stars anymore. We only are looking at the actions that we actually took at each time step. And we're comparing the upper confidence bound at that time step versus the real mean. But remember, the way we've defined our upper confidence bound, and put it over here, the way we defined our upper confidence bound, ut of at, is exactly equal to the empirical mean, at plus this square root 1 over 2n at log t squared over delta. Okay. And we said here that this was going to be the difference from Hofting between q of at minus q hat of at. So the probability that this, remember I called this u, the probability that this was greater than mu was small. Okay, so now we're assuming that all of our confidence bounds hold, which means that we know that the difference between the real empirical mean and the true mean of this arm is bounded by u. Yeah.
Sorry, going back a bit. For the leftmost bottom panel, sorry, it's a little hard to see. 2 questions. First of all, where does this second, so you have a union over I equals 1 the number of arms. I don't see where that index actually factors in. And then also, if you could just go over the third line with the delta over t squared and the summation, how we derive that.
Sure, yeah. So So what we did there is we said that if, are you asking about the second line to the third line? Yeah, so what we did that in this case is we said for each, we want to make sure that on each of the time steps, all of the upper confidence bounds hold. And so that's where we get an additional sum over here over all the arms. So this is conservative. Trying to make sure, we don't know, you could imagine just doing this over the arm that's selected, but we don't know which arm is selected. We want to be able to show, this is going to be a looser upper bound, saying this is sufficient. So we're saying that if you want to make sure that Q of A star is greater than the upper bound of the arm that is selected, it is sufficient to ensure that your upper confidence bounds are valid at all time points from this reasoning up here. And so this is the probability that your upper confidence bounds are correct on all time points. For every single time point, for every single arm, your upper confidence bounds have to hold. And then what we get in this case is we said that the probability on a particular time step, the upper confidence bounds holds, is delta over t squared. That's how we defined that U term. So that according to Hofting's inequality, it would hold with at least probability delta over t squared. And then, so this is that. And then I just made a side note that this is not something, some of you guys might have seen this, but I certainly wouldn't have expected people to, that just it turns out that in terms of the limit, if you sum over t equals 1 to infinity of t to the minus 2, that's bounded by pi squared over 6, which is less than 2. Fun fact. So you can plug that in, right? Because then you just get a 2 here, and then you just get a sum over all arms, which is m, and you have a delta. So this just allows us to take that infinite sum. So notice also that this goes to Chris's question before, this holds for the infinite horizon, because when we did this summing, we're basically making sure that our confidence bounds hold forever. So if we're, okay, great. So we said here now that we're doing all of this part under the assumption that our confidence bounds hold. Our confidence bounds hold mean that the difference between our expected mean and the true mean for that same arm is bounded by mu, bounded by u with high probability, where this is the definition of u. So that's what our Hofting inequality allowed us to stay. So take that quantity now, that's our u, and plug it in here. So this is looking exactly at the difference between our upper confidence bound and q. So this is exactly equal to sum over t equals 1 to t of u of 8. It's a little confusing in terms of notation. So I'll just plug in the exact expression right there. 1 over 2 nt of at log t squared over delta. Okay, so we've just plugged in that the difference between the empirical mean and the true mean is bounded by quantity u. Okay. All right, so then in this case, what we can do is we can split this up into the different arms that we pulled. Okay, so this is a sum over all time steps. We can pull out, note that this is, if we upper bound this by big T, this is equal to, less than or equal to square root log big T squared over delta. And then we're going to get a sum over all time steps, and we're going to split this up according to which arms we selected. Okay, so this is the same as if we look at for each of the arms, how many times did we pull it? So sum over n equals 1 to nti of square root 1 over n. So we just divided this up. Like for each of the arms, we selected them some amount of times. That's here. I is indexing our arms. So nti is the total number of times we selected arm I. And then we sum that up. Okay. And then if we note the fact that if you sum from n equals 1 to t square root 1 over n, that is less than or equal to 2 square root t. You use an integral argument for that. I'm happy to talk about it offline. Yeah, in the back.
What happened to that 1 over 2 in the untitled?
That was the 1 over 2.
Square root.
Thank you. We have a 2 here. We can put a 2 here. Thanks. I'll be a little loose with constants, but definitely catch me on that. Most of these bounds will all end up being about whether it's sublinear or linear. But it's good to be precise. Okay, so we have this quantity here. When is this quantity maximized? This quantity is going to be maximized if we pulled all arms an equal number of times. Why? Because 1 over n is decreasing with n. And so the largest these can be is if you split your pools across all arms equally. So if we go back up to here, I'm going to call this A. So A is going to be less than or equal to, square root 1 to log t squared over delta times sum over I equals 1 to m, sum over n equals 1 to t divided by m. So this is as if we split all of our pools equally across all the arms, 1 over square root n. Okay. And then we can use this expression. Okay, so this is less than or equal to 1 over 2. We're almost there. T squared over delta. And then we're going to get sum over I equals 1 to m of 2 square root t over m. Okay. And then when you sum this over m, you get less than or equal to square root 1 over 2 log t squared over delta. That brings an m into there. We're going to get like another 2 in here times tm. Okay. And now we're done. So what is this shown? This has shown that if we use upper confidence bounds, that the rate at which our regret grows is sublinear. Square root times a log. So t here is the number of timestamps. So time steps. So if we use upper confidence bounds in order to make our decisions, then the regret grows much slower. This is a problem-independent bound. It doesn't depend on the gaps. There's much nicer ones and tighter ones that depend on the gaps. But this indicates why optimism is fundamentally a sound thing to do in the case of bandits, is that it allows us to to have much better performance in terms of regret than it does for the E-greedy case. Yeah.
Can you just explain one more time the last line on the top board, how you went from summation over t equals 1 to big T, and you just pulled out the t squared as big T? What happened to t equals 1 to big T minus 1?
Great question. Yeah, so this log term here, t equals, is ranging from t equals 1 to t. This log term is maximized when t is big T. So we're upper bounding that log term, and then it becomes a constant, and we can pull it out. Okay. So the cool thing here is that this is sublinear. That's really the main point. I go through an example, and we'll go through more of this next time. We next go through an example for the toy domain for the broken toes of like what do these upper confidence bounds look like in that case, and then what will the algorithm do in these scenarios. So that's what we'll look at next, and then after that we'll look at, so this is sort of one class of techniques, which is this optimism under uncertainty approach, which is saying that we're going to look at what the value is based on a combination of the empirical rewards we've seen so far, plus an upper confidence bound over them, and use that to make decisions. And then the next thing we'll see too is where we are Bayesian about the world, and we instead maintain a prior, and we update our prior and use that to figure out how to act. So we'll go through this next week, and I'll see you then.